Why do some of the brightest lights we see in the night sky possess a mysterious bluish glow, almost electric, that sets them apart from the rest? The Milky Way, our cosmic home, harbors hundreds of billions of stars, but only a small fraction of them belong to that select group of bluish celestial bodies that seem to defy the laws of time and physics. These stars, true titans in the firmament, not only illuminate entire regions of space, but also hide fascinating stories about the origin and fate of the galaxy. When we look at the sky and notice that cold, bluish flash from some stars, we may not imagine the intensity of the processes occurring within them. Unlike our calm yellow sun, these stars live on the edge. They burn with such extreme temperatures that their color shifts towards blue, emitting energy on an almost inconceivable scale. Their life is a true cosmic sprint. They are born, evolve, and die at a dizzying speed compared to other stars. And during their short existence, they shape their surroundings in spectacular ways. But what makes them so special? Why is their color so different, and what does it really reveal about their nature? The blue of these stars is not accidental or merely a matter of appearance. It is the result of extreme physical conditions, a particular chemical composition, and an inevitable fate. Most bluish stars are destined to end their lives in titanic explosions, leaving behind remnants that will forever change the history of the galaxy. Exploring the universe of bluish stars is to delve into the most extreme natural laboratories that exist. They are the forges where the heaviest elements are made, the engines that drive galactic evolution, and the markers of time in the Milky Way. In this journey, we will discover why these stars, despite their rarity and brevity, are essential for understanding how our universe works and evolves. What secrets do these blue giants hold? What role do they play in the cycle of life and death of galaxies? Get ready to find out. What makes some stars in the universe shine with an intense, almost electric blue hue? Blue stars are true cosmic jewels, known for their fascinating color and impressive energy. But how do they really differ from other stars? To begin with, when we talk about blue stars, we refer to celestial bodies whose surface reaches extremely high temperatures, much greater than that of the sun. Their color is not a coincidence. Blue indicates that they are among the hottest in the observable universe, with surface temperatures that can exceed 30,000 Kelvin. Are these stars rare? Yes, and that rarity makes them even more interesting. Although we can see some bluish points in the night sky with the naked eye, they actually represent only a small fraction of all the stars in the Milky Way. Most of the celestial bodies we see in the sky are reddish or orange, much cooler. Blue stars, on the other hand, stand out not only for their color, but also for their size. They tend to be much more massive and voluminous than other more common stars like our sun. What other characteristics define these stars? In addition to their scorching temperature, blue stars exhibit spectra dominated by hydrogen and helium lines, allowing astronomers to distinguish them precisely through the analysis of their light. They are also usually extremely luminous. A single blue star can shine thousands of times brighter than the sun, illuminating entire regions of the galaxy. It's as if they are the spotlights of the cosmos, capable of transforming the environment around them. And why should we be fascinated by them? These stars are not only important for their spectacular appearance, but also because their existence is linked to places where the galaxy continues to form new generations of stars. Where there are blue stars, there is activity, youth, and change. They are, in a sense, markers of galactic vitality, beacons that indicate where the most recent chapters of the universe's history are being written. Thus, understanding what blue stars are is to peek into one of the most dynamic and powerful phenomena in our galaxy. Why do some stars shine with an intense blue color, while others appear red, orange, or even white? The answer lies in physics, specifically in the surface temperature of each star. It is not the material they are made of that determines their color, but the energy they emit due to their heat. In the case of blue stars, their temperature is so high that they radiate most of their light in the blue and ultraviolet regions of the spectrum. Thus, when we observe a blue star, we are actually seeing the result of millions of degrees of heat transformed into light. What accounts for this relationship between heat and color? Imagine heating a metal bar. It first glows in reddish tones, then turns orange, and if you continue to increase the temperature, it will shine bluish white. This same principle applies to stars, but on a much larger scale. Cooler stars, like red dwarfs, barely reach about 3,000 degrees on their surface, which is why they emit reddish light. But blue stars easily exceed 20,000 degrees, making them true cosmic furnaces. But why don't we see green stars in the sky if the temperature could make it possible? The answer is fascinating. The human eye perceives a mixture of colors emitted by the star. A star whose peak emission falls in the green actually also emits large amounts of light in blue and red, so our brain interprets its color as white. Only truly hot stars, those that concentrate their light in the blue, manage to stand out with that striking color. So, the color of a star is a direct fingerprint of its temperature. Blue stars are not only the hottest, but also the youngest and most massive. When we see their bluish glow, we are witnessing the spectacle of energy at its peak, a true luminous signature that reveals secrets about the physics and evolution of our universe. The simple act of observing the color of a star allows us, from Earth, to deduce fundamental data about its nature, its age, and its ultimate fate.
If you're enjoying this journey through the universe and want to keep exploring more cosmic mysteries, don't forget to subscribe to the channel and give the video a like. Thank you for being part of this star odyssey.
Among the most fascinating stars in our galaxy, O and B type stars hold a privileged place. What makes them so special within the vast stellar zoo? To answer, let's imagine a scale of colors and temperatures where stars are organized according to their heat and brightness. In that spectrum, O and B stars sit at the pinnacle. They are the hottest, brightest, and of course, the bluest. But how is their classification determined exactly, and why do they have such extreme characteristics? Stellar classification is primarily based on the analysis of the light spectrum emitted by each star. O and B type stars exhibit unique spectral lines, dominated by the presence of hydrogen and ionized helium. O type stars, in particular, show ionized helium lines and a surface temperature that can exceed 40,000 degrees Celsius, which is more than 6 times the surface temperature of the Sun. B-type stars, while slightly less hot, still reach impressive temperatures between 10,000 and 30,000 degrees Celsius. These figures are not only astonishing, but also explain why their dominant color is blue. The higher the temperature, the more their light shifts towards blue. But how can one distinguish an O star from a B star if both appear so similar at first glance? The difference lies not only in temperature, but also in mass and luminosity. O-type stars are true giants, with masses that can exceed 60 times that of the Sun and a luminosity that can be up to 1,000,000 times greater. B-type stars, while somewhat less massive and luminous, are still gigantic compared to most stars. If stars were light bulbs, O-type stars would be beacons shining in a dark night, while B-type stars would be powerful floodlights, illuminating their surroundings extraordinarily. An interesting curiosity is that, although O and B stars are extremely rare in number, they dominate the landscape of regions where new stars are born. Their intense ultraviolet radiation is capable of ionizing the surrounding gas, giving rise to spectacular nebulae and triggering the formation of new stars. Thus, on a cosmic scale, O and B stars act as engines of change and renewal in the galaxy. However, their life is as brief as it is intense. In just a few million years, they consume their fuel and leave behind indelible marks on the structure of the Milky Way. Why, if blue stars are so impressive and powerful, do they live such a short time compared to other stars? The answer lies in their very nature. These stars, while shining dazzlingly and dominating their surroundings with formidable energy, are doomed to a brief existence. To understand this, let's think of a campfire. If we pile up a lot of firewood and the fire burns at maximum intensity, it will consume itself quickly. The same happens with blue stars. They are gigantic nuclear factories that consume their fuel at a frantic pace. Blue stars are often tens of times more massive than the Sun. This great mass causes such high pressure and temperature in their core that nuclear fusion reactions accelerate enormously. As a result, they transform hydrogen into helium at impressive speeds, releasing colossal amounts of energy, which gives them that characteristic blue glow. However, this energy waste comes at a price. They exhaust their fuel in just a few million years, while a star like the Sun can live for several billion years. It's as if they are running a sprint instead of a marathon. Have you ever wondered what this means for the galaxy? The short life of blue stars implies that they are always tied to regions where star formation is recent. They don't have time to drift away from their birthplaces before fading away forever. That's why, when astronomers find a concentration of blue stars, they know that a stellar birth boom has occurred there in astronomically recent times. Moreover, their rapid evolution makes them key players in the chemical and structural changes of the galaxy. In the end, the fleeting existence of blue stars may seem like a disadvantage, but it actually makes them true engines of galactic evolution. When they die, they often do so explosively, enriching space with heavy elements and triggering new waves of star formation. Thus, although their life is short, their legacy endures in every corner of the Milky Way, marking the rhythm of cosmic history. What distinguishes a blue giant from a blue supergiant? The difference lies in their dimensions and their fate. Blue giants are massive stars, much larger and hotter than our Sun, but blue supergiants go even further. They can have tens or even hundreds of times the solar mass and shine with an intensity that defies imagination. If a blue giant is like a skyscraper compared to a house, a blue supergiant would be a colossal mountain in the middle of a city. Both are essential for understanding the life and death of the most extreme stars in the cosmos. But why are these gigantic blue stars so important? Their role goes far beyond illuminating the sky. Being so massive, they live fast and die young, leaving behind heavy chemical elements that enrich the interstellar medium. In other words, they function as gigantic cosmic furnaces that produce the material from which planets and even life itself are made. Without blue supergiants, the universe would be much poorer in elements like oxygen, carbon, or iron. Where can we find examples of these stellar colossi? One of the most well-known blue supergiants is Rigel, in the constellation Orion. Rigel shines with such intense light that, although it is hundreds of light years away, it is visible to the naked eye from Earth. Another fascinating case is the star Zeta Puppis, one of the most massive and hottest observed in our galaxy. These stars stand out not only for their size, but also for their strong stellar winds, capable of throwing enormous amounts of matter into space in a very short time, as if they were hurricanes unleashed on the star's surface. The life of a blue supergiant is a race against time. Due to their enormous mass, they burn their nuclear fuel at a dizzying rate. While a star like the Sun can live billions of years, a blue supergiant barely reaches a few million before exploding in a supernova. What's the result? The birth of even stranger objects, such as neutron stars or black holes. Thus, blue giants and supergiants are not only the brightest jewels of the galaxy, but also the precursors of some of the most extreme and mysterious phenomena in the universe. What makes blue stars shine with such immense intensity? The answer lies in their temperature and the amount of energy they release. These stars, which can reach surface temperatures of up to 40,000 degrees Celsius, radiate light and heat in a way that far surpasses our own Sun. In fact, some blue stars can be over 1,000,000 times more luminous than it. This extreme luminosity is not just an impressive fact, it is a key clue to understanding how these celestial bodies function and evolve. But why so much energy? It all has to do with the frantic pace at which they burn their fuel. Blue stars are gigantic nuclear factories, fusing hydrogen into helium at incredible speeds. This produces an enormous amount of pressure and heat, which in turn generates that characteristic blue light and a luminosity that can blind anyone who gets too close. If we could place one of these stars where the sun is, Earth would be scorched in a matter of seconds. Its brightness is so intense that, even being thousands of light years away, they can be visible from our planet. A fascinating fact is that the luminosity of a star does not grow proportionally to its mass, but in a much more exaggerated way. If one blue star has double the mass of another, it can be up to 16 times more luminous. This relationship, known as the luminosity law, explains why these stars stand out so much, even though they are far less numerous than cooler, reddish stars. It's like comparing a regular light bulb to a stadium spotlight. Even though there are many more light bulbs, the spotlight completely dominates the scene. This extreme luminosity has consequences. On one hand, it determines how long the star can live, as it consumes its fuel at a dizzying speed. On the other, it generates powerful stellar winds capable of stripping away the outer layers of the star and sculpting the space around it. Thus, the light and energy from these stars not only illuminate the cosmos, but also shape the evolution of their surroundings, leaving an indelible mark on the history of the galaxy. What does it take for a bluish star to be born, that type of bright and peculiar celestial body? The answer begins in the vast and cold stellar nurseries of our galaxy. There, inside gigantic clouds of gas and dust called molecular nebulae, gravity begins its silent but relentless work. These clouds, which can have hundreds of thousands of times the mass of the Sun, start to fragment and collapse under their own weight. But not all regions of these clouds give rise to common stars. There are especially dense areas rich in material, where the accumulation of mass is such that the ideal conditions for the birth of true giants are created, the future bluish stars. Why is it so difficult to form a bluish star, and not just a star like the Sun? The key lies in the amount of available matter. For a star to be blue, it must be born with a mass several times greater than that of the Sun. This means it needs to accumulate an enormous amount of gas in a very short time, before the intense radiation, once the protostar begins to shine, disperses the surrounding material and halts growth. It's like trying to build a mountain with wet sand before the wind comes and carries away the grains. This race against time makes bluish stars relatively rare, and they almost always form in the densest and most active areas of the galaxy. The regions where these stars are born are often teeming with other young stars, forming what astronomers call open clusters or stellar associations. In these environments, the proximity of multiple protostars favors gravitational collapse and the rapid growth of the most massive ones. However, the competition is fierce. The largest protostars can steal material from their neighbors, growing even faster and condemning the less fortunate to remain small and cold. It is a true cosmic battle for matter, where only a few manage to reach the critical mass to become bluish. Once the protostar reaches sufficient mass, the temperature in its core skyrockets to several million degrees. It is then that large-scale nuclear fusion ignites, releasing an enormous amount of energy that, in turn, emits intense ultraviolet radiation. This radiation not only gives it its characteristic blue hue, but also sweeps away the remaining gas around it, slowing the formation of new stars in the vicinity. Thus, the birth of a bluish star is not only the result of the accumulation of matter, but also the trigger for new cycles of life and death in the galactic neighborhood. Who would have thought that the formation of these stellar titans depends so much on speed and competition, as well as the simple accumulation of gas? What connection can the blue glow of certain stars have with the most mysterious clouds of the cosmos? If you have ever looked at photographs of space, you may have noticed regions wrapped in a faint pink glow. These are the so-called HI regions, true nurseries of stars and laboratories of galactic chemistry. But why do these areas seem to be so intimately linked with the hottest and bluest stars of the Milky Way? To understand this, we first need to know what an HII region is. Imagine a vast cloud of gas composed mainly of hydrogen, the most abundant element in the universe. When a bluish star, with its overflowing energy, is born in the heart of one of these clouds, its intense ultraviolet radiation strikes the surrounding hydrogen atoms and strips them of their electrons. This process, known as ionization, transforms neutral hydrogen into ionized hydrogen, or HII. It's as if the bluish star turned on a giant ultraviolet lamp, illuminating the cloud and making it glow in pink and red hues due to the recombination of protons and electrons. But why do only bluish stars achieve this effect? The answer lies in their temperature. These stars can exceed 20,000 degrees Celsius on their surface, emitting enough ultraviolet radiation to affect their surroundings. A cooler star, like our Sun, simply does not have the necessary power to create a significant HI region. Thus, the presence of an HI region is like a fingerprint. It indicates the nearby existence of one or more young massive blue stars. Moreover, HI regions are not only witnesses to stellar birth, but they also act as cosmic traffic lights. Their size and shape can reveal how many blue stars are inside them and how energetic they are. Sometimes, the pressure from the radiation and stellar winds of these stars can push the surrounding gas, shaping the cloud and triggering the formation of new generations of stars. It's a virtuous circle. Blue stars are born, transform their environment, and in doing so, pave the way for the birth of more stars. Finally, HII regions and their blue stars are vital for understanding the evolution of galaxies. Astronomers study them to measure star formation rates, analyze galactic chemistry, and track the places where the galaxy is renewing its inventory of stars. Thus, each HII region is much more than a bright cloud. It is the echo of the energy, youth, and power of the bluest stars, and a fascinating window into the perpetual cycle of cosmic creation. What is the real impact of blue stars on the evolution of the Milky Way? At first glance, it might seem that, being so few in number and living such a short time, their influence is limited. However, these stars, which burn with fierce intensity and extremely high temperatures, are true engines of change in our galaxy. Think of them as the great architects of a city. They are not the majority, but their works transform the environment for everyone. Blue stars, especially the most massive ones, produce enormous amounts of ultraviolet radiation. This radiation is capable of ionizing the hydrogen in the surrounding interstellar medium, generating bubbles of hot gas and HII regions. Why is this relevant? Because these processes not only illuminate the nebulae, but also trigger new waves of star formation. By compressing nearby gas clouds, the shock waves caused by their energy can sow the seeds for the birth of new generations of stars, perpetuating the cosmic cycle. But their role doesn't end there. When a massive blue star reaches the end of its life, its death is often spectacular, a supernova. This explosion is not only a bright and fleeting event, but it also releases heavy elements like oxygen, carbon, iron, and others, forged in its core, into space. Why is this fundamental for the galaxy? Because these elements enrich the interstellar medium, making it possible for planets, atmospheres, and eventually life as we know it to form. Without blue stars, the Milky Way would be much poorer in the essential ingredients for chemical complexity. Blue stars also influence the structure of the galaxy on a large scale. Their clusters often mark the spiral arms, those majestic luminous pathways that shape the Milky Way. Acting as beacons, they guide astronomers in mapping the galaxy and reveal where the most active star formation processes are occurring. Thus, although their existence is brief, the legacy of blue stars endures in every corner of our galaxy, shaping its chemistry, its form, and its evolutionary history. Have you ever heard of Wolf-Rayet stars? They are undoubtedly some of the most astonishing and enigmatic stars in our galaxy. You could say they are the superstars of the cosmos, not for their fame, but for their extreme characteristics. Wolf-Rayet stars stand out not only for their intense blue color, but also for their wild behavior and their short, explosive life. But what makes them so special, and why are they so fascinating to astronomers? Wolf-Rayet stars are true titans in the final phase of their existence. They are so massive that, instead of aging slowly, they lose mass at a dizzying rate, expelling enormous amounts of gas and dust into space. Their atmosphere is constantly torn apart by incredibly powerful stellar winds, which can reach speeds of millions of kilometers per hour. Imagine a storm so fierce that it strips entire layers from the star and hurls them into interstellar space. This intense mass loss exposes heavier elements like helium, carbon, and in some cases, oxygen, resulting in very peculiar spectra. Have you ever wondered how astronomers recognize a Wolf-Rayet star precisely by their unique spectra? Unlike other stars, Wolf-Rayet stars show very pronounced emission lines instead of absorption lines, revealing the presence of chemical elements that would normally be hidden beneath the stellar surface. Additionally, their luminosity is colossal. They shine tens of thousands of times brighter than the sun, even though their life is much shorter. To put it in perspective, if the sun lived like a person for 80 years, a Wolf-Rayet star would be like a celebrity that shines brightly but disappears before reaching 10. These stars are extremely rare. In the entire Milky Way, only a few hundred have been catalogued. Their scarcity is precisely due to the ephemeral nature of their existence and the exceptional conditions required for their formation. Only the most massive and hottest stars can become a Wolf-Rayet, and often their end is as explosive as their life. They are ideal candidates to become supernovae, and in the most extreme cases, even so-called hypernovae. To top it off, some gamma-ray bursts, the most energetic events in the universe, are suspected to be linked to the death of these blue giants. In short, Wolf-Rayet stars are natural laboratories where heavy elements are forged, and some of the most violent processes in the cosmos are unleashed. Their study helps us understand how massive stars enrich the interstellar medium and set the stage for the formation of new generations of stars and planets. If you ever wonder where the ingredients for life are born, don't forget to look towards these blue colossi. They are the most extreme alchemists in the galaxy. What does it mean for a star to be a blue hypergiant? Are we talking about simple luminous balls of gas or true cosmic monsters? Blue hypergiants are undoubtedly the most massive and colossal stars in the Milky Way. If the Sun is compared to a soccer ball, a blue hypergiant would be like an entire stadium. We are dealing with celestial bodies that can exceed more than 100 times the solar mass and reach diameters that defy imagination. But how do such extreme objects manage to exist? The key lies in the enormous amount of material they accumulate during their formation. These stars are born in regions rich in gas and dust, and they devour their surroundings at a dizzying speed. As a result of their tremendous mass, their cores reach temperatures and pressures so high that their luminosity becomes colossal. In fact, a single blue hypergiant can shine with the intensity of millions of suns combined. What does that imply? They are visible at incredible distances, serving as natural beacons in the farthest reaches of the galaxy. However, the life of a blue hypergiant is anything but tranquil. Their own brightness is a sign that they live on the edge. They consume their nuclear fuel at a frantic pace, which condemns them to a brief and tumultuous existence. While a star like the Sun can live for billions of years, a blue hypergiant barely reaches a few million before self-destructing. And what happens at the end of their life? Their fate is often a titanic explosion, a supernova that can give rise to stellar mass black holes. Famous examples of these gigantic celestial creatures are Eta Carinae and the star VY Canis Majoris. Eta Carinae, for example, has experienced eruptions so powerful that it became visible even to the naked eye during the 19th century, despite being over 7,500 light-years away. Why are they so rare? Because their formation requires exceptional conditions, and, due to their short life, it is unlikely to find them in advanced stages of evolution. Blue hypergiants, ultimately, are natural laboratories for understanding the limits of stellar physics and the most violent processes in the universe. Where do the most massive and brightest blue stars in the galaxy originate? The answer takes us to the most dynamic and turbulent corners of the Milky Way, the massive star formation regions. These places are not just scattered clouds, but true cosmic nurseries where gas and dust concentrate into dense clusters, ready to give rise to new and powerful stars. But what conditions make the birth of these blue giants possible, and why don't they emerge everywhere? For a massive blue star to form, a large amount of material must accumulate in a relatively small region of space. These areas, known as giant molecular clouds, can contain up to millions of times the mass of the Sun. Imagine a vast bank of cold, dark interstellar fog, where gravity gradually groups particles together until, at certain points, pressure and temperature soar. It is in those compact cores where the magic happens. Gravitational collapse initiates the process, and after hundreds of thousands of years, new stars are born, some so massive that their blue light soon dominates the surroundings. But why are these regions often found in the spiral arms of the galaxy? The explanation lies in the very structure of the Milky Way. The spiral arms act as galactic compressors. As they rotate, their density causes shock waves that compress gas and dust, stimulating the formation of new stars. That's why, if we could fly over the galaxy, we would see these arms filled with bright regions and glowing nebulae, direct evidence of the intense activity of forming blue and hot stars. Some of the most famous massive star formation regions are relatively close to us, such as the Orion Nebula or the W49 region, both brimming with young blue stars. In these places, the intense radiation and stellar winds from the newly born stars not only illuminate the surrounding gas, but can also trigger the formation of new stellar generations in a perpetual cycle of cosmic birth and transformation. Thus, massive star formation regions are the renewal engine of the galaxy, natural laboratories where matter is recycled and the spectacle of stellar life never ceases. Have you ever questioned why some stars live for millions of years while others barely survive a few million before disappearing? The secret lies in mass. In the stellar universe, mass is the decisive factor, the true architect of a star's fate. The more mass a star is born with, the faster it consumes its fuel and the shorter its existence. It's the cosmic equivalent of a candle. A small candle can burn for hours, but a huge, thick candle, despite its size, can burn out much faster if the wick is intense enough. But how does mass exactly affect the life cycle of a bluish star? Massive stars, like the blue ones, contain tens of times more mass than our Sun. This extra mass generates such high pressure and temperature in their core that nuclear fusion occurs at a frantic pace. Just like a sports car racing down a highway, mercilessly consuming gasoline, these stars burn their hydrogen in just a few million years. In contrast, less massive stars like the orange or red ones can live peacefully for billions of years, precisely because they consume their fuel sparingly. And what happens when a bluish star exhausts its fuel so quickly? The answer is dramatic. The enormous mass determines not only how quickly it lives, but also how it dies. Instead of a peaceful end, these stars experience titanic explosions, known as supernovae, that scatter heavy elements into the cosmos and can give rise to exotic objects like black holes or neutron stars. Thus, mass not only defines the duration of stellar life, but also the legacy it leaves behind after its death. A fascinating curiosity is that despite their brief life, massive bluish stars have a disproportionate impact on the evolution of their surroundings. Their intense radiation and powerful stellar winds shape nearby gas clouds, triggering the formation of new stars and enriching the interstellar medium with essential materials for planet and life creation. In summary, mass is the thread that runs through stellar existence. It determines how long a star will shine, how it will die, and what mark it will leave in the history of the galaxy. Did you know that in our own cosmic neighborhood, there exists a star cluster so bright and striking that it has fascinated humanity since ancient times? This is the Pleiades, also known as the Seven Sisters. But what makes this group of stars so special? Beyond their beauty in the night sky, the Pleiades are a natural laboratory for understanding how blue stars are born and evolve in the Milky Way. The Pleiades are primarily made up of young, hot stars, whose bluish light is the result of their extremely high surface temperature. If you have ever stopped to observe them, you may have noticed that they shine with an intensity that easily sets them apart from other nearby stars. Why does this happen? Because these stars of spectral type B are only about 100 million years old, which in astronomical terms is practically newborn. Their youth and great mass cause them to burn with overflowing energy, illuminating even the surrounding dust clouds, and generating the characteristic bluish glow that we can detect from Earth. But how did these stars come to group together in this way? The Pleiades emerged from the same giant molecular cloud. Imagine a huge cosmic incubator, where gas and dust collapsed under their own gravity, forming dozens of stars almost simultaneously. Unlike other clusters, the Pleiades are relatively close to us, about 400 light-years away. This makes them one of the most studied and accessible open clusters for astronomers. In fact, their proximity allows us to observe details such as gas disks around some of their stars, clear signs that planetary formation processes may still be occurring there. And what is the role of the Pleiades in modern astronomy? This cluster is key for calibrating distances in the galaxy, as its brightness and proximity serve as a reference for measuring other, more distant objects. Additionally, their study has revealed that blue stars are not only impressive for their appearance, but are also essential for understanding the evolution of star clusters and the dynamics of interstellar dust. The Pleiades, with their set of blue stars, invite us to look at the sky and question our own origins in the universe, reminding us that even the most beautiful groupings are, in essence, living laboratories of nature. Did you know that open clusters are true cosmic laboratories where blue stars display all their splendor? These clusters, formed by dozens or hundreds of stars born from the same cloud of gas and dust, often host some of the youngest and hottest stars in the universe. But why is it so common to find bluish stars in these clusters? The answer lies in their youth. Blue stars, being massive and short-lived, can only be found in places that still bear the fresh traces of star formation. When astronomers observe an open cluster and detect a predominance of bluish stars, they are looking at a recent photograph of the star birth process. It's like seeing a graduation class where the brightest and most energetic students stand out in the crowd. Blue stars, with their surface temperatures that can exceed 20,000 degrees Celsius, dominate the brightness of the cluster, even though they are actually a minority compared to the smaller, cooler stars that accompany them. However, their ultraviolet radiation is so intense that it can ionize the surrounding gas, leaving visible traces even after these stars have vanished. But what do these open clusters reveal about the evolution of blue stars? By studying their composition and age, scientists can better understand how massive stars are born, evolve, and die. In many cases, open clusters act as cosmic clocks. The presence of blue stars indicates that the cluster is young, generally less than 200 million years old, since after that time the most massive stars explode as supernovae or transform into compact objects like neutron stars or black holes. Thus, the quantity and type of blue stars present in a cluster is a key clue to estimating its age. And what happens when we observe open clusters without blue stars? In that case, we are likely looking at older groupings, where the massive stars have already disappeared and only longer-lived, cooler stars remain, such as red or yellow dwarfs. Therefore, the study of blue stars in open clusters is not only fundamental for understanding the life of the hottest stars, but also for deciphering the history and evolution of the cluster itself. Ultimately, these clusters are a privileged window to look at the recent past of our galaxy and understand the cycles of starbirth and death that shape it. The Orion Nebula, one of the most iconic and studied regions of the sky, is much more than a cloud of gas and dust visible to the naked eye on clear nights. What makes this place so special in astronomy? The answer lies in the bluish stars that illuminate it and transform its surroundings. At the heart of the nebula is the famous trapezium cluster, a group of young massive stars that emit an intensely bluish light, a result of their extremely high surface temperature. These stars are true cosmic beacons, capable of ionizing the gas around them and causing the nebula to shine spectacularly. Why are these stars so blue? The explanation lies in the physics of light. The most massive stars burn their fuel at dizzying speeds, reaching surface temperatures exceeding 20,000 degrees Celsius. The hotter a star is, the bluer its light. Thus, in the Orion Nebula, the presence of O and B spectral type stars turns this region into a true natural laboratory for studying the birth and early life of the most powerful stars in the universe. These stars stand out not only for their color, but also for their ability to shape the environment. Their ultraviolet radiation is so intense that it strips electrons from hydrogen atoms, creating a sea of ionized gas that glows brightly, what astronomers call an HII region. Have you ever wondered how the presence of these bluish stars affects the formation of new stars within the nebula itself? The process is as dynamic as it is fascinating. Stellar winds and radiation from the most massive stars can compress the surrounding gas clouds, triggering the collapse of new regions and the birth of even younger stars. It's as if these pioneering stars not only illuminate their surroundings, but also give the first push to the next generations, in a chain of cosmic creation that never stops. The Orion Nebula is, therefore, a privileged stage where stellar life and death intertwine in a perpetual cycle. The bluish stars residing within it are young, bright, and ephemeral, but their impact is disproportionate. Their light reveals the structure of the nebula, their energy shapes the interstellar medium, and their explosive end, as supernovae, sows the elements necessary for the formation of new worlds. Observing this corner of the universe reminds us how, in a simple diffuse spot in the sky, lies all the creative and destructive power of the most extraordinary stars in the galaxy. What fate awaits a blue star from the moment it is born until its spectacular end? It all begins in a dense cloud of gas and dust, where gravity starts to compress the matter and a dizzying process is unleashed. If the cloud is massive enough, the pressure and temperature in its core grow to the point where nuclear fusion ignites. Thus, a blue star is born, young, bright, and extremely hot, ready to consume its fuel at an impressive rate. But why do these stars live so little time compared to others? The answer lies in their voracious appetite. The more massive the star, the faster it burns its hydrogen, like a sports car guzzling gasoline at full speed. During its adult life, the blue star remains stable, fusing hydrogen into helium in its core. This stage, known as the main sequence, is its longest period, although for a blue star this may mean just a few million years. In comparison, the Sun, much less massive, will live in the main sequence for billions of years. But for a blue star, time runs in a kind of cosmic fast-forward. The intensity of its radiation and its surface temperature, which can exceed 30,000 degrees Celsius, make it one of the most imposing luminaries in the galaxy. Its light is so energetic that it can ionize the gas around it, sculpting nebulae and generating regions of intense star formation. What happens when the hydrogen in the core runs out? The blue star begins a dramatic transformation. The core, no longer having enough pressure to counteract gravity, starts to collapse. Then, the star may expand and become a blue supergiant, or, in some cases, a red supergiant, depending on its exact mass. Here begins a frantic race in which helium and other heavier elements fuse in the core, in increasingly brief and chaotic stages. the balance becomes more and more delicate. It's like watching a huge candle burning so intensely that it is destined to go out soon. Finally, the outcome is as spectacular as it is brief. When the nuclear fuel runs out and there is no way to support the core against gravity, the blue star violently collapses and triggers a supernova. This explosion releases into space all the elements formed in the stellar core, enriching the galactic environment and sowing the ingredients for new generations of stars and planets. Depending on its original mass, the final remnant can be a neutron star or a black hole, true remnants of a blue star's life. Thus, although its existence is fleeting, the life cycle of a blue star is crucial for cosmic recycling and the evolution of the galaxy. Isn't it amazing to think that the life and death of these celestial giants are directly related to the existence of everything we know? What happens when a bluish star, so massive and bright, reaches the end of its life? The answer is one of the most spectacular transformations in the universe, the supernova. Bluish stars, due to their great mass, live fast and die young. But their farewell is neither silent nor discreet. On the contrary, it is a cosmic explosion so intense that, for a brief moment, a single star can shine brighter than an entire galaxy. How is it possible that an object, which has been fusing atoms in its core for millions of years, ends in an explosion of such magnitude? The key lies in the delicate balance between the gravity trying to collapse the star and the pressure generated by nuclear reactions at its center. For most of its life, the star maintains this balance, first fusing hydrogen, and then heavier elements like helium, carbon, and oxygen. However, there comes a time when the core fills with iron, an element that cannot release energy through fusion. It is then that the star loses its internal support. In a matter of seconds, the core collapses under its own weight, and the outer layers are violently expelled into space. That is the moment when the supernova is born, releasing an amount of energy that is hard to imagine. It is estimated that, in those brief seconds, it radiates as much energy as the sun does over its entire lifetime. But what do these explosions mean for the universe? Supernovas are not just spectacles of light and energy. They are true cosmic furnaces where the heaviest elements like gold and uranium are forged. In fact, all the calcium in our bones and the iron in our blood come from ancient supernovas. It is fascinating to think that, thanks to the violent death of a bluish star, matter is recycled and sows space with the necessary ingredients for new generations of stars, planets, and even life. Thus, the explosive end of a massive star is, paradoxically, the origin of many other things in the cosmos. Not all stars end their lives in such a dramatic way. Only the most massive have the privilege, or the curse, of starring in a supernova. After the explosion, what remains at the center can become a neutron star, or, if the mass is sufficient, a black hole. These compact remnants are part of the legacy that the bluish star leaves to the universe. Isn't it surprising to think that, in the death of these celestial giants, lies the secret of our own origin? When we gaze at the night sky and contemplate the grandeur of the stars, we are reminded that, ultimately, we all share the legacy of a supernova. What happens when a massive blue star reaches the end of its life? The outcome is as spectacular as it is decisive for the fate of the cosmos. When these giants exhaust the fuel in their core, gravity takes control and triggers a catastrophic collapse. But what remains after that titanic explosion? The answers lead us to the most extreme and mysterious objects in the universe: black holes and neutron stars. A neutron star is the compact remnant that remains when the mass of the original star is not enough to form a black hole. Imagine compressing the mass of our sun into a sphere just 20 kilometers in diameter. The result would be an unimaginable density where a teaspoon of matter would weigh more than a mountain. These stars, composed almost exclusively of neutrons, can spin hundreds of times per second and emit powerful pulses of radiation, making them the famous pulsars. But why don't all massive stars end up this way? When the original star is even more massive, gravity is so intense that nothing can halt the collapse. This is how a black hole is born, a region of space where gravity is so strong that not even light can escape. Black holes are not cosmic vacuums that devour everything around them, but they do represent the points of no return in the universe. Their presence is revealed by the effects they cause in their surroundings, disks of accelerated material and jets of energy that can outshine entire galaxies. Both neutron stars and black holes are natural laboratories of extreme physics. There, the known laws are put to the test, and phenomena arise that challenge our understanding, such as degenerate matter, colossal magnetic fields, and the curvature of space-time. Could these remnants be the key to understanding the deepest secrets of the universe? Every time a blue star ends its life this way, the cosmos presents us with a new mystery and also a tool to explore its most unknown frontiers. What makes blue stars so fleeting compared to other stars in the sky? This is one of the great paradoxes of the universe. The stars that shine the brightest, dominating their surroundings with their dazzling blue light, are also the ones that remain active for the shortest time. To understand this, we must delve into the heart of these stellar giants. Blue stars, primarily of types O and B, possess masses between 10 and over 100 times that of the Sun. However, despite their colossal size, their lifespan is astonishingly brief. Why does this happen? The answer lies in their voracious consumption of nuclear fuel. Blue stars burn hydrogen at a frantic pace, as if they were race car engines running at full power without rest. For example, while a star like the Sun can live for nearly 10 billion years, a massive blue star barely survives a few million years, a tiny fraction on the cosmic scale. It's like comparing a slowly burning candle to a torch that blazes with extreme intensity, consuming itself much faster. But what consequences does this short life have? One of the most notable is that blue stars are only found in places where star formation is relatively recent. If we observe a star cluster and see blue stars, we know that cluster is young. In contrast, in older clusters, the blue stars have disappeared, leaving only the longer-lived and less massive stars, like the reddish ones. Thus, blue stars become cosmic clocks, marking the passage of time in the regions where they are born. Despite their brief existence, blue stars leave indelible marks on the galaxy. During their short lives, they inject enormous amounts of energy into the interstellar medium through stellar winds and intense radiation. And when their end comes, they often explode as supernovae, seeding the cosmos with heavy elements and giving rise to exotic objects like black holes and neutron stars. Thus, although their light fades quickly, the impact of blue stars endures for billions of years, reminding us of the importance of the ephemeral in the evolution of the universe. What would happen if a star rotated so fast that it literally began to shed part of itself? Such are the B stars, one of the most fascinating and mysterious types among the blue stars in our galaxy. Their name is no coincidence. The letter B corresponds to their spectral type, while the E refers to the presence of emission lines in their spectrum, a clue that something very unusual is happening around them. But what makes these stars so special? The key lies in their rotation speed. B stars spin at such extreme velocities that, in some cases, their surface can reach hundreds of kilometers per second. To put it in perspective, if Earth rotated at the same speed as a B star, a day would last only a few minutes. This dizzying rotation has dramatic consequences. The material from the star's outer layers is ejected into space, forming a thin equatorial gas disk that surrounds the star like a bright, ethereal ring. And how do we know that disk is there? The presence of the disk is revealed through the emission lines in the star's spectrum. While most stars show absorption lines, B stars exhibit emission lines, a clear signal that there is hot, diffuse gas orbiting around them. These lines not only allow us to confirm the existence of the disk, but also provide information about the chemical composition and dynamics of the expelled material. This phenomenon raises truly intriguing questions. Why do some blue stars develop these disks, while others do not. It all points to the fact that the rotation speed must come very close to the limit, where the centrifugal force equals the star's gravity. In that delicate balance, any disturbance, such as internal pulsations or the influence of a nearby stellar companion, can be enough for the B star to lose part of its mass and feed the disk. This cycle of material expulsion and reaccretion can repeat several times throughout the star's life, generating variations in brightness and characteristics of the disk, making B stars exceptional cosmic laboratories for studying extreme stellar physics. Moreover, these disks are not permanent. They can form and fade over time. B stars are, in essence, stars that live on the edge, challenging stability and revealing how far nature can go under extreme conditions. Thanks to their uniqueness, they have captured the attention of astronomers worldwide, and many mysteries remain to be solved regarding their origin, evolution, and ultimate fate. B stars remind us that even among the brightest and hottest celestial bodies, there is always room for the unexpected. How hot can a star get? If you think the sun is already extremely hot, get ready to meet the true titans of temperature in the Milky Way. The hottest known stars are like cosmic ovens, where matter and energy merge in an explosive ballet that defies imagination. But what does it really mean for a star to be hot? In astronomy, we talk about surface temperatures that can exceed 40,000 degrees Celsius, unimaginable values in any earthly environment. These stars, mostly belonging to spectral types O and some Wolf-Rayet, emit such bluish and bright light that, if they could be placed in the sun's position, they would make Earth uninhabitable in a matter of seconds. For example, the star WR102, a Wolf-Rayet located in the constellation Sagittarius, is considered one of the hottest stars ever observed, with estimated surface temperatures around 200,000 degrees Celsius. To put it into perspective, that's more than 30 times the surface temperature of the Sun. How do they reach such extreme values? The secret lies in their mass and internal composition. The hottest stars tend to be gigantic, with masses tens of times greater than that of the Sun. This enormous mass generates such high internal pressure and temperature that nuclear fusion processes unleash with unprecedented violence. The result? Enormous amounts of energy that radiate primarily in the ultraviolet range, invisible to our eyes, but devastating for any nearby form of life. Moreover, many of these stars have stellar winds so intense that they lose matter at incredible speeds, literally saying goodbye to themselves into space. But why don't we see so many stars like this in the night sky if they are so luminous? The answer is surprising. They live very little time, just a few million years. Their brightness is so intense and their fuel consumption so rapid that they quickly exhaust their life, often ending in explosive supernova or leaving behind exotic objects like black holes or neutron stars. Thus, the hottest stars are like cosmic fireworks, brief, spectacular, and fundamental for the evolution of the galaxy. The search for these stars not only reveals extreme data, but also helps us understand the early moments of the universe's history. By studying their properties, astronomers gain clues about the formation of heavy elements and the dynamics of galaxies. Is it possible to find even hotter stars? That is one of the great open questions, and each new discovery brings us a little closer to understanding how the most powerful engines of the cosmos work. What would happen if a blue star, as bright as a galactic lighthouse, suddenly changed its intensity before our eyes? This phenomenon, far from being a mere oddity, is the signature of what are known as blue variable stars. But what does it really mean for a star to be variable? In short, these are stars whose brightness fluctuates perceptibly over time. Not all blue stars are constant and predictable. Some seem to have their own pulse, alternating between moments of maximum splendor and phases of dimmer light. This variability can be as subtle as a faint blink or so dramatic that the star nearly disappears from view before reappearing with renewed strength. Why does this curious behavior occur? There are several causes, but one of the most fascinating relates to internal processes. Pulsations on the star's surface. Imagine a massive blue star as a gigantic cosmic boiler, where the energy generated in its core causes periodic expansions and contractions of its outer layers. This ebb and flow can alter the amount of light emitted, creating cycles of brightness that can last from a few days to several months. A notable example of this type of star is the Beta Cephei variables, true astronomical clocks whose heartbeat can be recorded even with modest instruments from Earth. However, pulsations are not the only cause of variability in blue stars. There are blue variable stars whose behavior is due to external factors, such as the presence of a nearby stellar companion. In binary systems, two stars orbit each other, and if one of them is blue and massive, its companion can partially or totally eclipse it during its orbit, causing regular and predictable drops in observed brightness. In other cases, the culprit is a gas disk surrounding the star, as is the case with some B stars. When this disk thickens or dissipates, the light we see from Earth changes, sometimes unpredictably. But beyond curiosity, why are blue variable stars important? The answer is fascinating. These celestial bodies are true natural laboratories that allow astronomers to investigate the most extreme physical processes in the universe. By measuring and analyzing their variation cycles, scientists can deduce details about the size, mass, internal composition, and evolution of these blue giants. Some even serve as distance indicators, helping to map the structure of the Milky Way. Thus, every fluctuation of light in a blue variable star is a valuable clue, another piece in the enormous puzzle of modern astronomy. Finally, one might wonder, could our own sun become a variable star? The answer is no, at least not in the spectacular way that blue giants do. The variability of blue stars is a direct consequence of their enormous mass, temperature, and cosmic youth. They remind us that, in the universe, even the most seemingly stable objects can hide surprising and mysterious dynamics. Blue variable stars are ultimately a demonstration that life in the cosmos is far from monotonous. It is a vibrant and sometimes unpredictable spectacle. What happens when a bluish star, with its tremendous energy, lives in the heart of the galaxy? To understand this, one must first imagine the interstellar medium as a kind of cosmic ocean, filled with gas, dust, and scattered particles. Bluish stars, with their extreme intensity and temperature, act as cosmic engines that stir and transform this ocean. But how do these stars manage to modify their surroundings on such colossal scales? The key lies in the ultraviolet radiation they emit, thousands of times more intense than that of our sun. This radiation is capable of ionizing the hydrogen present in the interstellar medium, that is, stripping electrons from atoms and creating regions of plasma known as HII regions. These bubbles of ionized gas not only shine brightly, but also mark active zones where star formation can be accelerated or at times halted. It's as if a bluish star lit a beacon in space, altering the balance and physical processes around it. But that's not all. Bluish stars also unleash powerful stellar winds, streams of particles moving at speeds of hundreds or even thousands of kilometers per second. These winds sweep away gas and dust, sculpting massive cavities and bubbles in the interstellar medium. What impact does this have? On one hand, these explosions of energy and matter can trigger the birth of new stars by compressing nearby gas clouds. On the other hand, they can disperse material and hinder star formation in certain areas, demonstrating that the role of these stars is both creative and destructive. At the end of their brief but intense lives, bluish stars culminate in supernova explosions, releasing heavy elements and energy in enormous quantities. These events seed the interstellar medium with essential materials for the formation of planets and future generations of stars. Thus, they not only transform their immediate environment, but also contribute to the chemical and dynamic evolution of the entire galaxy. Who would have thought that the life and death of a blue star could determine the fate of entire regions in the Milky Way? The influence of these blue giants is undoubtedly one of the hidden engines that shape our universe. What do some of the brightest and hottest stars in the galaxy have in common? They are so young and massive that they rarely appear alone. This is where the fascinating concept of OB associations comes into play. But what does that acronym really mean? The letters O and B correspond to the spectral types of stars that exhibit intense bluish colors, extremely high temperatures, and fleeting lifespans. OB associations are groupings of dozens or even hundreds of these stars, born almost simultaneously in regions rich in gas and dust. If we think of the galaxy as a large city, these associations would be like bustling neighborhoods filled with energetic youth who, sooner or later, transform their surroundings. Why do OB stars tend to form in groups rather than in isolation? The answer lies in the very nature of their birth. Giant molecular clouds, true stellar nurseries, collapse under their own gravity and give rise to bursts of star formation. The most massive stars, like those of types O and B, require enormous amounts of material for their gestation, something that can only be found in these extreme environments. And since these clouds often fragment into multiple cores, the result is a brood of enormous stars being born almost simultaneously, a phenomenon that astronomers call massive star formation. What happens after these stars are born? Their lives, although short, are anything but quiet. O and B stars flood their surroundings with ultraviolet radiation and powerful stellar winds, sculpting bubbles in the surrounding gas and triggering new waves of star formation. Moreover, these stars do not remain bound forever. OB associations are very loosely gravitationally bound structures. Over the course of a few million years, most of their members are dispersed throughout the galaxy, as if a gust of wind were to dismantle a house of cards. However, during that brief period, these associations leave a deep imprint on the galactic structure and chemistry. What about chains of OB stars? Sometimes, OB associations are not found in isolation, but are distributed across large regions of the galaxy, forming chains that can extend for hundreds of light years. These patterns, called OB belts or chains of OB associations, often outline the spiral arms of the Milky Way. Thus, the most massive blue stars act as beacons that signal the highways of recent star formation in the galaxy. Their study is key to understanding how the spiral arms are shaped and how the galaxy recycles its raw materials to create new generations of stars. In summary, OB associations and chains are natural laboratories where extreme physics unfolds on a grand scale. They are witnesses to galactic youth, marking the pulse of star formation and defining the cosmic landscape with their energy and transience. Without these concentrations of bluish stars, the Milky Way would be a much quieter, less dynamic, and undoubtedly less spectacular place. What do blue stars reveal about the history of the Milky Way? Although they appear as simple bright dots in the sky, these stars are true capsules of galactic time. Their appearance, distribution, and disappearance mark the most dynamic chapters in the evolution of our galaxy. But why are they so important for understanding the past and present of the Milky Way? The answer lies in their relationship with large-scale stellar formation and transformation processes. Bluish stars, with their fleeting life and intense luminosity, serve as indicators of regions where star formation has occurred recently. If the galaxy were a book, blue stars would be the newly written pages. Their presence signals the places where giant clouds of gas and dust have condensed to give life to new generations of stars. Where blue stars shine today, just a few million years ago, darkness and interstellar silence reigned. That's why, when astronomers locate clusters or associations of blue stars, they can reconstruct the chronology of the most recent events in the Milky Way. Have you ever wondered how we know when and where the galaxy has experienced its most active episodes? Blue stars are the key. Due to their short lifespan, they can only be found near their birthplaces. Thus, their distribution reveals the spiral arms and starburst areas, but it also allows tracking gas migrations and collisions between interstellar clouds. It's as if these stars draw the roots of creation and change on the galactic map. Moreover, These stars have been fundamental engines of chemical transformation in the Milky Way. When they end their lives in spectacular supernovae, bluish stars enrich the interstellar medium with heavy elements, essential for the formation of new stars, planets, and even life. Without them, the galaxy would be much poorer and more monotonous. That's why scientists study blue stars, not only to understand what the Milky Way is like today, but also to unravel how it has changed and evolved over billions of years. Blue stars, ultimately, are both witnesses and protagonists of the fascinating history of our galaxy. When we think of blue stars, we often imagine them as part of the bustling spiral arms of the Milky Way, where gas and dust cluster to give rise to new stellar generations. But is it possible to find these blue jewels outside the galactic disk, in the less dense and more solitary outskirts of our galaxy? The answer, surprisingly, is yes. Although most blue stars are born in regions rich in interstellar material, astronomers have detected specimens in places as unexpected as the galactic halo and other peripheral areas, where the conditions for star formation seem much less favorable. What mechanisms could lead a blue star to end up in these seemingly inhospitable environments? One of the most intriguing explanations is the phenomenon of runaway stars. Imagine a game of cosmic billiards. In dense star clusters, gravitational interactions can fling a star at enormous speeds, ejecting it far from the galaxy's main disk. Some of these blue stars, known as hypervelocity stars, even manage to completely escape the Milky Way's gravitational pull, traveling into intergalactic space. However, others become trapped in eccentric orbits that take them through the galactic halo for millions of years. Is there evidence of blue star formation directly in the halo or other external regions? Although it is very rare, isolated cases have been observed where small clouds of gas, possibly remnants of ancient galactic mergers or tidal streams, have collapsed to form young stars, some of which turn out to be blue. These events are exceptional, but they demonstrate that the Milky Way is a dynamic system, where encounters and mergers with satellite galaxies can sow new stellar seeds even in the most remote places. What do these stars teach us about galactic history? Their presence in the halo is a valuable clue about the violent and chaotic processes that have shaped the galaxy. Some blue stars in the outer regions may be relics of dwarf galaxies absorbed by the Milky Way, carrying with them young stellar populations and enriching the halo with their characteristic light. Furthermore, studying their chemical composition and movement allows astronomers to reconstruct the galaxy's past, as if they were silent witnesses to ancient migrations and cosmic encounters. Thus, blue stars outside the disk not only challenge our ideas about where they can be born, but also become essential signals for unraveling the complex history of the Milky Way. What would happen if a star were expelled from its galaxy at such an extraordinary speed that it could cover unimaginable distances in just a few million years? This is how hypervelocity blue stars are born, true cosmic bullets that challenge our understanding of the universe. But how can a star, much more massive than our Sun, reach such extreme speeds to escape the gravitational embrace of the Milky Way? The key lies in extreme encounters with supermassive black holes. When a binary system of blue stars gets too close to the center of the galaxy, the supermassive black hole can capture one of the stars and fling the other away at a tremendous speed, as if it were a stone thrown by a cosmic slingshot. This phenomenon was theoretically predicted in the 1980s and confirmed decades later when astronomers detected stars traveling at hundreds and even thousands of kilometers per second, surpassing the escape velocity of the galaxy. It's as if a star received such a strong kick that nothing could stop it. But what sets a hypervelocity blue star apart from other rogue stars? Besides their speed, these stars are usually young and massive, making them shine with an intense blue color. Their origin in central or dense regions of the galaxy makes them privileged witnesses to extreme phenomena. However, their fate is tragic. They advance alone into the intergalactic void, drifting further away from any source of gas or dust that could fuel their evolution. Their life, already short due to their blue and massive nature, becomes a solitary and irreversible journey. And how do we know that these stars are really fleeing the galaxy? Thanks to modern telescopes and missions like Gaia, it is possible to measure the movement of these stars in space with great precision. Astronomers have identified trajectories that point directly from the galactic center outward, confirming their violent expulsion. It is estimated that there may be a few dozen known hypervelocity stars in the Milky Way, but there are likely many more, invisible to our instruments. In a way, these hypervelocity blue stars are messengers of the most dramatic events in the universe, reminding us that the galaxy is far from a serene and peaceful place. Have you ever wondered why not all blue stars shine the same, or why in some regions of the galaxy they seem to be rarer? The answer has a lot to do with a fundamental concept in astrophysics: metallicity. In astronomy, metals are not just iron or gold, but all elements heavier than hydrogen and helium. Metallicity is, then, the proportion of these elements in a star. And while it may sound like a technical detail, metallicity has a profound impact on the formation and evolution of blue stars. Why does metallicity matter for the birth of a blue star? Massive stars, which are the ones that typically exhibit that characteristic blue color, form in regions where the gas is relatively clean, or, in other words, has few metals. When a gas cloud contains many metals, it cools more quickly, favoring the formation of less massive and cooler stars. In contrast, in regions of low metallicity, the gas remains hotter and lighter, allowing true blue giants to form. That's why in young galaxies or in the halo of the Milky Way, where metals are scarce, blue stars can reach extreme masses and temperatures. But metallicity not only affects birth, it also determines the fate of these stars. A blue star with high metallicity will lose mass more quickly due to intense stellar winds driven by the pressure of metals in its atmosphere. It's like a car having more holes in the gas tank. It will run out of fuel sooner. Conversely, a blue star with low metallicity retains more mass during its life, which can lead it to explode as an even more powerful supernova, or even form a larger black hole. This relationship between metallicity and stellar evolution has fascinating implications for the history of the Milky Way. By analyzing the metallicity of blue stars, astronomers can reconstruct the chemistry of the interstellar gas over time and understand how the galaxy has been enriching its material. It's like reading an ancient diary where each page reveals the secrets of past generations of stars. Thus, metallicity is not just a number in a table. It is the key to understanding why blue stars are the way they are and how they have silently influenced the fate of our galaxy. What makes blue stars special, turning them into true cosmic clocks? Their brief life and intense brightness not only fascinate with their spectacularity, but also play a fundamental role for those trying to decipher the history of the Milky Way. If a region of space is populated by bluish stars, it means that there has been recent star formation there, because these stars barely survive a few million years before disappearing in a great explosion. Why is this so important for astronomers? Because by observing where these stars are located, it is possible to reconstruct the recent past of the galaxy, as if it were fresh tracks in the snow. Blue stars function like the hands of a galactic clock. Wherever they shine brightly, we know that the star factory has been active recently. If we observe a distant galaxy and distinguish clusters of blue stars, we can deduce that those places are, or were until recently, true nurseries of stars. It's like looking at a city at night and seeing the lights on in certain neighborhoods. Those areas are full of activity. When blue stars disappear from a region, it indicates that star formation has stopped there millions of years ago, and what remains are older, redder stars. But how is this knowledge used to measure galactic time? Scientists compare the number of blue stars with stars of other colors and types. If blue stars predominate, the age of the cluster or region is very young, just a few million years. If only red or yellow stars remain, then the place is hundreds or even billions of years old. Thus, bluish stars allow us to map the timelines of the Milky Way and other galaxies, identifying young areas and distinguishing them from the older corners of the universe. Moreover, Blue stars also help date cosmic events such as galaxy collisions or massive bursts of star formation. For example, if a swarm of blue stars is detected in an area where there weren't any before, that could be the signal of a recent collision with another galaxy, which has triggered the formation of new stars. In other words, these stars are witnesses and chroniclers of the most important galactic events. Without them, it would be much more difficult to reconstruct the history of our galaxy and understand the secret rhythms of the cosmos. Why do blue stars seem to prefer the spiral arms of the Milky Way? When we observe our galaxy from afar, its spiral arms stand out like rivers of light, filled with clouds of gas, dust, and above all, young and massive stars. But what makes this structure special, turning it into the favorite cradle of blue stars? The answer lies in galactic dynamics and the ephemeral nature of these stars. Blue stars are true cosmic sprinters. They are born, shine brightly, and disappear in just a few million years. This time is insignificant compared to the lifespan of other stars, like our Sun. As a result, blue stars have little opportunity to drift far from where they were born. And those places, in the Milky Way, are mainly concentrated in the spiral arms. Why? Because that's where the ideal conditions for forming new stars come together. Dense clouds of cold hydrogen and the ebb and flow of density waves which compress the gas and trigger star formation. We could imagine the spiral arms as enormous galactic factories where new stars are constantly being assembled. Each time a density wave passes through the galaxy's disk, it compresses the gas clouds and triggers bursts of starbirth. In this process, the most massive and hottest stars emerge, the ones that shine with that characteristic blue hue. Their intense radiation and fleeting lives make them act as luminous markers of the exact place where, at that moment, the galaxy is giving birth to new stellar generations. And what does this reveal about the structure of the Milky Way? The presence of blue stars allows astronomers to trace the design of the spiral arms, even in regions where interstellar dust obscures the light of other less bright stars. Thus, the blue color of these young giants not only adorns the galaxy, but also becomes an essential tool for understanding its architecture. Each blue star is, in a way, a beacon that signals the vibrant pulse of star formation in the spiral arms, helping us decipher the invisible map of our galaxy. Have you ever wondered if blue stars, those gigantic luminaries that burn fiercely in the cosmos, can have planets around them? The answer is much more complex than it seems. The formation of planets depends on a delicate choreography between the leftover material after a star's birth and the time that star remains stable. But blue stars, with their rapid life and overflowing energy, challenge that choreography. Is it possible for worlds like Earth to arise in their environment? Blue stars, especially those of types O and B, are true cosmic furnaces. Their extreme temperature and luminosity generate strong stellar winds and powerful ultraviolet radiation emissions. This environment can be compared to trying to build sandcastles in the middle of a hurricane. The gas and dust disks surrounding these stars, the material needed to form planets, are often swept away before solid bodies can consolidate. Moreover, the life of a blue star is so short, sometimes just a few million years, that planets would find it almost impossible to complete their formation process. However, nature never ceases to surprise us. Protoplanetary disks have been detected around some young blue stars, suggesting that, at least in theory, planet formation could begin. But what kind of planets could survive in such a hostile environment? If they managed to form, they would be worlds bathed in intense radiation, exposed to devastating stellar winds, and likely doomed to a brief existence before the parent star exploded as a supernova. Imagining a stable planetary system around a blue star is, for now, more science fiction than reality. Still, the role of blue stars in planet formation goes far beyond their own systems. When these stars die, they enrich space with heavy elements, such as oxygen, carbon, and iron, essential ingredients for the formation of new planets, and perhaps for life itself. Thus, although planets around blue stars are extremely rare, the legacy of these stars is vital. They set the stage for future stellar generations, where worlds like ours can be born under more benign conditions. Who would have thought that, despite their fleeting existence, blue stars sow the seed for the creation of new universes? What happens when two bluish stars get so close that they can't help but dance around each other? Double and binary stars are much more common than we often imagine, and when both companions are bluish, the astronomical spectacle is even more fascinating. These systems, formed by two stars orbiting a common center of gravity, test the limits of stellar physics and help us understand how gravitational interaction can change the fate of colossal celestial bodies. Why is it so interesting to study binary systems of blue stars? The answer lies in mass and energy. Bluish stars, being much more massive than the Sun, live fast and die young. But in pairs, their lives can change drastically. Sometimes, one of the stars may steal material from its companion, literally absorbing part of its mass and altering its own evolution. This process, known as mass transfer, can cause a star that was destined to age quickly to receive a second youth by gaining fresh fuel. Can you imagine if humans could rejuvenate thanks to the energy of another? In many of these systems, the proximity between the stars is so extreme that stellar winds collide, generating violent storms of radiation and magnetic fields. This interaction can produce exotic phenomena such as X-ray bursts or the formation of gas disks around one of the stars. Moreover, in certain cases, the stars may eventually merge into a single one, resulting in an even more massive and luminous star, a true blue monster in the galaxy. Binary systems of bluish stars are also essential for understanding some of the most energetic events in the universe, such as double supernova or the formation of binary black holes. When both stars end their lives explosively, the result can be the creation of pairs of compact objects that, while orbiting each other, emit gravitational waves detectable even millions of light years away. Thus, the study of these cosmic pairs not only reveals the secrets of stellar life and death, but also connects us with the most extreme and mysterious phenomena of the cosmos. What if I told you that in some of the oldest star clusters in the galaxy, there are blue stars that shouldn't be there? This enigma has puzzled astronomers for decades. These stars, known as blue stragglers, seem to defy the laws of stellar evolution. While the other stars in the cluster age and become cooler and redder, they shine with an intense blue hue, as if they were much younger. How is it possible that in an environment where no new stars are forming, these exceptions arise that seem to have rejuvenated? To understand this mystery, let's imagine a grand dance where all the participants age at the same pace. Suddenly, some appear to turn back time, rejuvenating before everyone's eyes. The blue stragglers are those dancers who, against all logic, look younger than their peers. But where do they get this unexpected vigor? The answer points to the interaction between stars. In dense globular clusters, stars are so close to each other that they can merge or exchange mass. When two stars merge, the resulting new star can gain more mass and therefore a higher temperature, becoming blue and bright. Another possibility is that one star robs material from a nearby companion, revitalizing itself and appearing as a newly formed star. This process of stellar rejuvenation is fascinating because it challenges the traditional idea that all stars in a cluster are born and evolve together, following a single timeline. The blue stragglers demonstrate that stellar life can be much more dynamic and chaotic than it appears. Furthermore, their presence offers astronomers a unique opportunity to study stellar interaction phenomena, such as mass transfer and mergers, in extremely ancient environments. But why so much attention to these stars? Blue stragglers are not only an enigma in themselves, but they also serve as natural laboratories to understand the limits and exceptions in stellar evolution. By analyzing them, scientists can reconstruct the history of the clusters they inhabit, deciphering past interactions and predicting the final fate of these groups of stars. Thus, the mystery of blue stragglers reminds us that, even in the oldest and quietest places in the universe, life can find surprising ways to reinvent itself. How can we study stars that are thousands of light years away and that, at first glance, only appear as blue dots in the sky? Observing blue stars from Earth is a true scientific challenge, but thanks to technology and human curiosity, we now know a lot about these enigmatic celestial bodies. For centuries, astronomers have used optical telescopes to capture their light, but it's not enough to just look. It's essential to analyze that light, break it down, and uncover the secrets it carries through space. Did you know that each blue star has a kind of luminous fingerprint? This is achieved through spectroscopy, a technique that allows us to separate starlight into its component colors and thus identify chemical elements, temperature, and speed. It's like listening to an orchestra and distinguishing each instrument separately. Modern spectroscopes, attached to giant telescopes like those at Mauna Kea or Paranal, provide astonishing details, from the composition of the stellar atmosphere to the presence of magnetic fields and supersonic winds. However, the Earth's atmosphere can hinder the precise observation of blue stars. That's why astronomers have devised clever solutions. How can we prevent the shimmering air from distorting the image? One answer is adaptive optics, a technology that adjusts the telescope mirrors in real time to compensate for atmospheric turbulence. Another solution has been to launch telescopes into space, like the legendary Hubble, which can observe in wavelengths invisible from the Earth's surface and capture the ultraviolet light from the hottest stars. In addition to visible light, scientists explore the blue universe in other frequencies: X-rays, infrared, and radio. Why observe in so many bands? Each reveals different facets of these stars, from violent eruptions to disks of material swirling around them. Thus, the observation of blue stars becomes a multidisciplinary endeavor, where physics, engineering, and a passion for the cosmos combine to unveil the mysteries of some of the most fascinating objects in the galaxy. Why do blue stars hold such a special place in modern astrophysics? The answer lies in their extreme nature and their role as cosmic laboratories. These stars, with surface temperatures exceeding 20,000 degrees Celsius, are true natural particle accelerators. Their intense ultraviolet radiation not only illuminates vast regions of space, but also triggers fundamental physical and chemical processes in the interstellar medium. Analyzing how they interact with their environment allows us to understand how matter evolves in the galaxy and how new generations of stars and planets arise. But how have they revolutionized our knowledge about stellar life and death? Blue stars have short lifespans, but they burn with tremendous force. Their life cycle, much faster than that of stars like the Sun, enables scientists to observe astrophysical phenomena in fast forward that would otherwise take millions of years to study. Each time one of these stars explodes in a supernova, it seeds space with heavy elements, the true building blocks for planet formation and, potentially, for life. Therefore, understanding the fate of blue stars is key to deciphering the chemical history of the universe. Blue stars have also been indispensable tools for measuring cosmic distances. Thanks to their extremely high luminosity, they can be observed thousands or even millions of light years away, acting as beacons that mark the structure and scale of the galaxy. Researchers have used clusters of blue stars to calculate the age of galactic regions and to trace movements of dark matter, the mysterious substance that makes up a significant portion of the cosmos. Thus, these stars not only tell us their own story, but also that of the Milky Way and its deepest secrets. And what about their influence on technology and astronomical observation? The need to study the extreme properties of blue stars has driven the development of more sensitive and precise instruments, from space telescopes to X-ray and ultraviolet detectors. Thus, the challenge of understanding these celestial giants has generated innovations that benefit all of modern astronomy. In summary, blue stars are much more than mere bright points in the sky. They are the key pieces that help us unravel the mysteries of the universe and advance, step by step, in the scientific knowledge of our galaxy. How hot can a blue star get? To find the answer, we just need to observe the most extreme stars known in the Milky Way. Some, like those of Type 03, reach surface temperatures exceeding 40,000 degrees Celsius. To put it in perspective, that's almost 7 times the surface temperature of the Sun. But there are even more impressive cases. Wolf-Rayet stars have been identified with estimated temperatures exceeding 200,000 degrees. These figures challenge the imagination and remind us that, in the universe, the extreme is the norm for these giants. Did you know that there are stars so luminous that if they replaced the Sun, life on Earth simply could not exist? For example, blue hypergiants like Eta Carinae can shine with the intensity of several million suns combined. Their light is so powerful that, in addition to illuminating vast regions of space, it sweeps away everything around it with stellar winds at speeds of thousands of kilometers per second. These winds can expel in just 1 year an amount of matter equivalent to several times the mass of our Sun. Thus, they not only shine brightly, but literally disintegrate at an astonishing rate. And what about speed? Some extreme blue stars have been detected moving at such high speeds that they are about to escape the Milky Way. They are known as hypervelocity stars. How do they achieve such a feat? It usually happens when one of these stars is part of a binary system and its companion explodes as a supernova. The explosion can propel the remaining blue star to speeds exceeding 1,000 kilometers per second, sending it on a solitary journey into intergalactic space. In astronomical terms, it's like throwing a stone so fast that it completely escapes the gravitational field of the galaxy. Another fascinating curiosity is the rarity of extreme blue stars. Despite their spectacular nature, they are incredibly scarce. If we could compare the stellar population of the Milky Way to a city, extreme blue stars would be like skyscrapers, imposing, but very few compared to the multitude of low-rise buildings that represent the smaller, longer-lived stars. This is because the life of these stars is as brief as it is intense. They are born, shine, and die in just a few million years, a minimal fraction on the cosmic scale. Finally, it is intriguing to think that some of these extreme stars could end their existence collapsing into stellar mass black holes, or even leaving behind supernovas so powerful that they enrich space with heavy elements. It is astonishing how, in the brevity of their lives, the most extreme blue stars leave an indelible mark on the history and evolution of the galaxy. What does the future hold for the study of blue stars in our galaxy? Until recently, we relied on optical telescopes and ground-based observatories, but today, the research on these stars is about to undergo a genuine revolution. New generations of space telescopes, like the James Webb, allow us to observe the cosmos in infrared and ultraviolet wavelengths, penetrating through interstellar dust and revealing clusters of blue stars that were previously hidden. Thanks to these technologies, astronomers can accurately analyze the composition, age, and formation environment of these stars, thus obtaining answers to enigmas that have intrigued science for decades. Is it possible to predict the fate of a blue star before it explodes into a supernova? Advances in computer simulations are helping to model the life cycle of these luminous giants. By comparing real data with theoretical models, scientists can more accurately anticipate when and how a blue star will collapse, or whether it will leave behind a black hole or a neutron star. This type of prediction is not only valuable for astrophysics, but also helps to better understand the chemical and dynamic evolution of the Milky Way. Will new instruments be able to detect blue stars in even more distant galaxies? The future of research points towards the study of blue stars outside our galaxy, allowing for comparisons of their formation and evolution in different cosmic environments. Projects like the Extremely Large Telescope, currently under construction in Chile, promise unprecedented resolution for identifying and analyzing massive stars in distant clusters. This is crucial for answering one of the deepest questions in astronomy. Are blue stars a universal phenomenon or exclusive to certain galactic regions? Finally, missions dedicated to observing the universe in X-rays and gamma rays are being developed, such as the upcoming Athena mission. These tools will allow us to capture the extreme behavior of blue stars, their stellar winds, and the most energetic explosions in the cosmos. Additionally, artificial intelligence will play a key role in analyzing large volumes of data, identifying patterns and exceptions that might go unnoticed at first glance. With each advance, we get a little closer to the heart of these cosmic titans, opening the door to discoveries that, until recently, seemed like mere science fiction. What would the galaxy be without the fleeting and dazzling presence of blue stars? These colossal forges of light and energy, although they live a short time compared to other stars, have a gigantic impact on the evolution of the cosmos. They are like the fireworks of the Milky Way. They appear, illuminate their surroundings, and leave their mark forever. Their intense radiation, stellar winds, and final explosions shape the interstellar gas and dust, paving the way for the formation of new generations of stars and planets. Without them, the galaxy would be a much quieter and less vibrant place. Did you know that the blue color of these stars is a sign of extreme temperatures, much higher than those of our own sun? Blue stars can exceed 30,000 degrees, emitting such bright light that, despite being thousands of light years away, they can dominate the landscape of a star cluster. It's as if a stadium spotlight suddenly appeared in a city of warm lights, impossible to ignore. But that intensity comes at a price. They consume their nuclear fuel so quickly that they barely live a few million years, while other stars can last billions. But why are we so fascinated by these stars? Beyond their color and brightness, blue stars tell us stories about the youth of the galaxy, about regions where matter stirs and transforms. They are witnesses to the most energetic processes in the universe, and when they explode as supernovae, they scatter heavy elements that will be the raw material for future planets, perhaps even for life itself. Blue stars are the alchemists of the cosmos, forever changing the chemistry of their surroundings. Could we understand the history of the Milky Way without paying attention to these stars? The answer is a resounding no. Blue stars are key to deciphering the past, present, and future of our galaxy. They teach us that, although life may be brief, it can leave an indelible mark. So, every time you look up at the sky and see a blue star, remember that you are witnessing one of the most powerful and ephemeral engines of the universe, leading actors in the cosmic drama that has shaped our galactic home.